Okay, let's start with question number 8 from the first two units, chapter 1 and chapter 2. And this question is asked in June 2017 regarding the capacitance of a parallel plate capacitor. Let's solve this. It says in a parallel plate capacitor with air between the plates has an area of 8 into 10 to the power minus 3 meters square. So parallel plate capacitor with air between the plates has an area. So area of parallel plate capacitor A is equal to 8 into 10 to the power minus 3 meters square. And distance between the plates is 2 millimeter. That is D is equal to 2 into 10 to the power minus 3 milli. I am converting it to meter. So 10 to the power minus 3. Calculate the capacitance of the capacitor. So you have to calculate the capacitance. That's the first part of the question, and it continues. If this capacitor is connected to a 50 volt supply, so now this capacitor is connected to a 50 volt supply. What is the charge on each plate of the capacitor? So we need to find out the charge on each plate of the capacitor. So let's find out the capacitance first. But we have formula connecting these three equations, that is C is equal to A epsilon naught divided by D. So area 8 into 10 to the power minus 3, epsilon naught permittivity of free space, that is 8.854 into 10 to the power minus 12 whole divided by distance 2 into 10 to the power minus 3. So this value, 2 ones are, this 4s are. So let's solve this. 16 carry 1, 20, 1 carry 2, 32, 34 carry 3, again 32 plus 3, so 35.416 into 10 to the power minus 12. The capacitance unit is farad. You can also write as 35.416. 10 to the power minus 12 refers to picofarad. So we calculated the capacitance. And it also asks us, so now this capacitor is connected to a potential of 50 volt supply. 50 volt supply. What is the charge? So we have capacitance, potential and Q. So the equation relating them is Q is equal to C into V. So this becomes 35.416 into 10 to the power minus 12 and multiplied by 50. On solving this, we get the value 35.416 into 50 will be equal to 1770.8 into 10 to the power minus 12. So this can be written as 1, 2, 3. I am reducing it to, so 1.77 into 10 to the power minus 9 coulomb or 1.77 nano coulomb. So Q is equal to 1.77 nano coulomb. 10 to the power minus 9 means nano. So we get 1.77 nano coulomb. So it's a very simple numerical for 5 marks. They are asking us to calculate the capacitance with air between the plates, and if this capacitor is connected to the potential difference of 50 volt supply, so what is the charge stored on that? So we have calculated both the values. Let's move on to the next question. Okay, let's start with the question number 9 from the first two units. So this question is asked in March 2018. Very conceptual. and is from the first chapter regarding the electric field. Let's start with this. Three charges each of equal to plus 4 nanocoulomb are placed at the three corners of a square of side 2 centimeters. So three charges equal to plus 4 nanocoulomb are placed at the three corners of a square of side 2 centimeter. Okay, first I take a square. And I call this as A, B, C, and let it be D. Of square of side 2 centimeter. So this is 2 centimeters. So 2 into 10 to the power minus 2 meter we can convert. Find the electric field at the fourth corner. So we have to find out the electric field at fourth corner, that is at D, due to this charges at A, B, C. So what I have here 4 nanocoulomb is also 4 nanocoulomb, and here also I have plus 4 nanocoulomb. So three equal charges placed at the corners A, B, C. So we need to find the electric field at the corner D. So first, in order to find out the electric field at corner D, what we need to imagine is we need to imagine a test charge. Let us say a test charge Q0 is there at D, and let us find out the resultant electric field due to these three individual charges. So plus 4 nanocoulomb and Q0, if you observe, this is positive and it's also positive. The resultant electric field due to plus 4 nanocoulomb at A with respect to D will be in this direction. The resultant electric field at D due to A, so I call this one as ED, electric field at D due to A. Similarly, plus 4 nanocoulomb, and that's positive, Q0 is also positive. The resultant electric field at D due to the charge plus 4 nanocoulomb will be along the diagonal, and it will be in this direction. So I call this one as electric field at D due to B. In the same way, plus 4 nanocoulomb, so the resultant will be in this direction. This is, I call it as electric field at D due to C. So diagram plays a very important role in solving this electric field numerical. So what we need to do is, one I have EDB and the other two is EDA and EDC. So what we can do is, if I find out the resultant of EDA and EDC using the parallelogram law of vector addition, that is EDA and EDC, they are making an angle of 90 degree. So we will find out the resultant of EDA and EDC using the parallelogram law of vector addition. So they will result here, that is, I call it as the resultant of EDA and EDC, I call it as EAC, that is electric field at D due to A and C. Now we can see that the resultant, the final two electric field are in the same direction by finding out the values of EAC and EDB. So we can able to calculate the electric field at the D. That's the procedure. Solve for EDC and EDA, then EDB, then finally adding up EDB and EAC will be the resultant electric field. Let's start from one by one. EDA, you can also see EDA is equal to EDC. Since the electric field depends upon, if I write a general equation, E is equal to KQ divided by R square, you can see that electric field depends upon the charge and the distance. With respect to EDA, the charge at A is 4 nanocoulomb and distance is 2 centimeter. Similarly, the charge at C is 4 nanocoulomb and the distance is 2 centimeter. So they can be written as EDA will be equal to EDC, which is equal to K into any of the charge divided by square. So that is side square. So this comes out to be 9 into 10 to the power 9 to 4 into 10 to the power minus 9 and 2 centimeter square. So 2 centimeter r is equal to, it can be written as 2 into 10 to the power minus 2 meter. So squaring it, but I get 4 into 10 to the power minus 4. So this one and 10 to the power 9, 10 to the power minus 9 will be equal to 1 and I'm left with 9. So they cancel out. Minus 4 which is upwards becomes 10 to the power 4 Newton per Coulomb. That is EDA is equal to EDC. The resultant, sorry, the electric field at D due to A and C is this much. Let's find out EDB, that is electric field at D due to B. So I calculate here EDB is equal to K QB divided by, this is the diagonal, so I write it as BD square. So K, that is 9 into 10 to the power 9, P 4 into 10 to the power minus 9, so the charge all divided by BD square. See, BD is the hypotenuse if you consider the triangle BCD. So what happens? 4 into 10 to the power minus 4, 4 into 10 to the power minus 4, that is 8 into 10 to the power minus 4. Answer we get it as square root of, okay, directly if I write BD square is equal to, from this I write BD square is equal to BC square plus DC square. So that is 4 into 10 to the power minus 4 plus 4 into 10 to the power minus 4. So this comes out to be 8 into 10 to the power minus 4. What is that? BD square, directly BD square, I write it there. So I get 8 into 10 to the power minus 4. On solving it, so this is 1's up, 2's up, so I get 4.5 into 10 to the power plus 4. So minus 4 shifts upwards becomes plus 4. 10 to the power 9 minus 9. So the result is 1. So 4.5 into 10 to the power 4 Newton per Coulomb. So we have calculated the individual values of the electric field at D due to A, B and C. Next we need to find out the resultant of electric field at D due to A and D due to C. So they are in different direction, resolving these two vectors into one using parallelogram law, vector addition. The formula I have is, okay, electric field at D due to AC, which can be written as square root of E D A square plus E DC square plus 2 EDA EDC cos theta. And you can see theta from the diagram, the angle between EDA and EDC, that is 90 degree. Angle between theta is the angle between EDA and EDC, 90 degree. So cos 90 is equal to 0. This entire value will tend to 0. Then I am left with EDA square root of EDA square, that is 81 into 10 to the power 8 plus 81 into 10 to the power 8. So we have calculated the magnitude of the electric field at D. Let's find out the direction. For that we have tan alpha is equal to E DC cos theta, sorry, sin theta divided by E DA plus E DC cos theta. So EDC, the value is 9 into 10 to the power 4 sin 90, that is the angle between EDA and EDC. So sin 90 is 1 whole divided by EDC. So that's also 9 into 10 to the power 4 and plus EDC cos 90, that will be 0. So I get only this. Then I'm left with 1, which implies alpha is equal to 45 degree, because tan inverse of 1 is 45 degree. So we get alpha is equal to 45 degree. That's the angle between EDA and the resultant electric field ED. So we have calculated both in magnitude